This, for example, is an article written in 2008 by Chris Anderson, who at the time was the editor of Wired magazine. So a very smart guy, but I disagree with this piece here. And what it says is that the end of theory of the data deluge makes the scientific method obsolete. The idea here is that you can conquer everything by brute force alone. If you have a data set with millions or billions or trillions of observations, then you don't really need theory, you don't really need experience, that things become self-evident when you have that much data on your hands. I think this idea is actually misleading, maybe even a little bit dangerous at the margin. Consider, for example, when he wrote this article, it was in the summer of 2008, where in the United States, many other parts of the world, we were in the midst of a catastrophic financial collapse. In part because of bad modeling. Good data, but bad modeling. The banks and the rating agencies that looked at the prices of mortgage-backed securities, for example, and ensured mom-and-pop investors that they were very safe. They had data from millions of American mortgages, but they made some very flawed assumptions about how they might behave when housing prices began to decline. They assumed, for example, you could have isolated regional effects. So if you buy a mortgage in California, it wouldn't be correlated with a mortgage in New York instead. And of course, that wasn't true, and almost all these securities that were rated as being very safe instead would be downgraded or defaulted instead. They are relatively simple conceptually, but they involve using a lot of data in a simple way and processing those results quickly. But conceptually, there are really three major things going on with the model, and the three steps are outlined here. So the first idea is that you want to look for an average of the polls. And of course, an average is maybe the most simple statistical tool available, but it still cuts against the instincts of a lot of the media when they cover politics. Typically what happens during an election campaign in the US, we have very, very abundant polling. You might not call it a big data environment, but we do have literally thousands of polls that are released over the course of a presidential campaign. In the US, of course, we have an electoral college system, so a lot of the state-by-state data is very useful. But what happens sometimes, say you have 20 polls in a row showing President Obama up in a state, say my state like Michigan, for example, which he won. Then a 21st poll comes out and shows Mitt Romney ahead instead. A poll that's probably an outlier. Inevitably, the headlines in the paper will focus on the outlying result. That makes for a better headline. No, Romney's making a comeback. And really, it's probably a bad poll, a fluky result that should be more or less ignored instead. So just focusing on the average, and there's some technique here. How far do you want to go back? How quickly do you want to adjust? But the principle is very simple, looking for the consensus in the data. The second idea is what I call count to 270. So the name of my website, 538, is the number of electoral college votes in the US. To win a majority electoral college, you need 270 electoral votes. And so it's a matter of looking at the permutations and combinations of different states. Of course, in the US, with all our diversity, we do have regional effects. So, for example, neighboring states like Michigan, Wisconsin tend to vote the same way, maybe differently than a vote in another part of the country might go. But the program is just looking at all the different possible permutations and combinations of states and doing that very quickly and efficiently. But again, the principle isn't that complex. It's just a matter of using good software to do this in a more reliable and automated and faster way. And finally, the last idea is accounting for the margin of error or the uncertainty in the prediction. Or I should say, really, I think of there's this term prediction, this term forecasting. I prefer the term forecasting instead, in the way that weather forecasters use the term, meaning that it's probabilistic. We're not saying we're sure of anything, although there are some things, we have some very conservative states, for example. In Utah, probably our most conservative state, was almost sure that Mitt Romney would win. In a state like Massachusetts, very liberal, 100% or 99.999 that Obama would win. But some states are very close, no matter how much data you have. Florida, for example, a classic swing state, where on election morning last year, our model had Obama with a 50.2% chance, I think, of winning Florida. So basically, for all intents and purposes, a toss-up. But one thing I found is that when you talk in the language of probability, it's not intuitive for many people. If you say 51%, people assume that means much more likely than 50%. If you say something's 80%, they think that means it's certain. So to give you one example, if you play Russian roulette, you have an 83% chance of surviving a round of Russian roulette. Meaningfully different than almost certain when you have those types of stakes. So use your imagination and pretend that this, instead of an ugly PowerPoint slide, is a beautiful river in North Dakota. North Dakota, of course, borders Manitoba and Saskatchewan. I think very cold up there, so you have a lot of snowfall every winter, which means in the spring it finally thaws, the snow begins to melt, and you have the risk of flooding in the streams and rivers there every year. 1997 had been an especially snowy winter in the Midwest. Our National Weather Service was concerned, therefore, about flooding along the banks of the Red River, which went through Grand Forks, North Dakota, and they issued a prediction saying that the floodwaters would crest at 49 feet on their worst day. So people there weren't that worried. They had flood walls that went up to 51 feet instead, so something to keep an eye on, but almost no one bothered to buy insurance, for example. What the Weather Service failed to tell people there is that the margin of error on their forecast was plus or minus 9 feet. They were afraid that if they conveyed uncertainty in the outlook, that people wouldn't trust the forecast at all. When instead, all the useful information was in that margin for uncertainty. And in fact, the waters would crest at 53 feet, so well within the confidence interval, the margin of error. Not bad, only a 10% miss. They made this forecast weeks in advance, but still, almost all the town was flooded. You couldn't have prevented the flood, but you could have at least insured the properties, and said you needed billions and billions of dollars in federal and state money for a bailout instead. And as I said earlier, if you're in a business context, if you're in a political context, then certainty sells, but in a forecasting context, dealing with difficult environments in real time, then being able to hedge your bets and think probabilistically is the more helpful technique instead. When you see poker on TV, though, this is a screen capture from ESPN, they actually show you what card your opponent has, as though you have X-ray vision. So this is a famous hand where Chris Moneymaker was in fact bluffing, right, and the other player, Sam Farha, folded. So you see it on TV, you're like, oh, this game is so easy. The guy's bluffing, of course. How can these pros not know that? But if you do have X-ray vision, then poker is a pretty easy game to play. They also show you some very interesting back rooms in the casino if they find out that you have X-ray vision as a device. But anyway, people watching poker on TV came to a false impression about how easy poker was to beat, and as a result, I was able to win some of their money for a period of time. During this period, of course, we did data guided some data mining on how much money each player at the table was winning or losing over the long run. So on online poker tables, typically you had 10 players, and this represents their long-term win rates in US dollars. So I found, first of all, that this was an asymmetric pattern where it's really a lot easier to be really bad at something than really good at something. So the best player at the table is making $100 an hour. Not bad for playing poker, but the worst player is losing about $420 an hour instead. This guy probably is a guy, is so bad. If he just folded every hand, he would only lose $200 an hour. Twice as bad by trying. The lesson here, though, is that you kind of get from this to this rather boring PowerPoint slide instead, which is an 80-20 curve, which shows that you get diminishing returns as you add complexity, as you add learning to your model or to your theory. Very often, the first 20% of data will get you a long way. So in poker, for example, you go from playing like totally naively to just using a few basic rules. So you say, for example, well, I'm gonna fold with my bad hands and call with my medium strength hands and raise with my good hands. Then that's not a bad rule set. Probably 80% of the time that gets you to the right answer, and you can go from being really terrible at poker to just break even, perhaps, instead. And it's almost the case now where finally teams have learned in baseball. We're now in this post-Moneyball era, almost all teams employ some type of data scientist, analyst on their payroll. They realize that if you don't like this stuff, if everyone else is doing it and you're not even trying, you're going to get caught with all the players that you're overplaying for instead. So if you can't be a thought leader as a business, then you have to play catch up later on just to tread water pretty much. But yeah, it's businesses that are using analytics, I think, are going to put themselves in an advantageous place.